All right, let's do some work energy problems. I made these problems up, so they might be silly, but I'm going to go over the solution. So let me tell you the problem, and then we'll get to work. So this says a mass bead. See, there's your problem right there. That's really weird. It's a mass that is also a bead on a straight frictionless track. And so I did that. It's kind of like this. Here's a wire, right? So it's a bead, so it's constrained to move in a straight line. Okay, so maybe I didn't say that right. So the bead has a mass. Let's just write down the stuff we know. Bead has a mass of 0.5 kilograms, so it's kind of heavy. And moves from a position, I'll call that position 1, R1, is negative 0.5, 0.1, 0 meters. To position 2, I'll call that R2, is 0.7, 0.4, 0 meters. And there is a force, which I cut that off, F equals 0.5, 0.10 newtons is applied. So if it starts from rest, I'll go ahead and say that V1 magnitude equals 0 meters per second. What's the velocity, speed, or the magnitude of velocity at the second position? So what's V2? Question. Okay, there's a problem. We got it. So let's just draw a picture really quick. So it starts from this position. If I just draw an XY axis, which doesn't even really matter, it starts like right here, and then it goes to R is 0.7, 0.4, so it goes something up like this. So this is R1, and this is R2. And that's important because we really need delta R. Delta R is going to be R2 minus R1. Why do we need that? Let's start from the beginning and talk about why we need that. And this has to do with the work energy principle. This says that the work is the change in energy. If I have the system of just the bead, and there is no gravitational force here, I wasn't clear on that, but I should have added that in space. This is in space. Space. So we don't have to worry about gravitational force. So the system's the bead, then the work done will be the work done by this force, and we define work as F dot delta R, and that's going to be change in energy, and the only kind of energy we have is kinetic energy. So that's why we need to find that displacement delta R. I already have the vector force F, so if I take that, that'll give me the work, and I can use that to find the change in kinetic energy, which is K2 minus K1. But since it starts from rest, K1 is 0. So you can see where we're going here. That's why I need to find delta R, the displacement. And if you want to draw this force, I mean, the force looks something like, sort of like this. It doesn't have to be in the same direction, and I actually didn't even try. Now, you might say, well, couldn't I find the angle between those? Couldn't I say work equals F delta R cosine theta? Absolutely. But how do you find the angle between this and this displacement? Is not so easy. Okay, so in fact, I just don't even want to do that. Okay, let's get delta R. Delta R is R2 minus R1. So it's going to be, I'll write it out, R2 of 0.7 minus negative 0.5, so plus 0.5, 0.4 minus 0.1, and then 0 minus 0. And that's going to be 1.2, 0.3, 0 meters. So there's my delta R vector. Now I can find the work. Work is F dot delta R. So how do you do the dot product? The dot product is simply the multiplicative product of the x components plus the product of the y components plus the z components, and then add them all together. So I'm going to say the x component of fx, which is 0.05, I'm going to leave off the units, times the x component of delta R, which is 1.2, plus the x component of the y component of f, 0.1, times the y component of delta R is 0.3, plus 0 times 0. So let's just put this in my calculator. This is a scalar value, right? So if I turn this on with my calculator, I'm going to say, I could probably do this without the calculator. 0.5 times 1.2 is, I know that's 0.6. And then that's 0.03 times plus times 0.01 is 0.03, but I'll do it anyway. 0.1 times 0.3 equals, and then I can just, oh, I can add that. So 6.63 joules. And that is the change in kinetic energy. So here I have delta K equals 0.63 equals K2 minus K1. We already said K1 is 0. So this is going to be equal to K2, which is 1/2 mv2 squared. So I know the mass, I can solve for the velocity. So v2 squared is going to be equal to 2 times 0.63 divided by the mass of 0.5. And then I can take the square root of both sides. And there's my speed. So let's do that. Okay, so I have clear square root, not good with calculators, 2 times 0.63 divided by 0.5, and I get 1.59. Now, it's important to realize that a couple things. One, does the wire exert a force on this bead? It has to, right? Because in order to constrain it along this path. But I didn't include the work done by the wire, because if it's frictionless, then this wire can only exert a force perpendicular to the wire. And so let's call that N. So here is, let's say, N. Here's delta R. And the angle between those is always 90 degrees. And the cosine of 90 is 0. So if there is a constraint force on this bead from the wire, it will have 0 work done on the particle. It will not contribute to the change in kinetic energy. The other important thing is that this gives me the final speed of the particle. It does not give me the final velocity vector. I mean, it's technically possible to get that. I could say the velocity is in the same direction as delta R, and I could find that unit vector. So you could say V2 vector is V2 times delta R hat. But I'm not going to do that. Okay, but you could. But in general, the work energy principle doesn't give you a velocity answer. But it's easier than using Newton's second law. Why would you use work energy in this case? The key here is if you have a displacement, if you're dealing with a change in position and you don't care about time, you're probably going to want to use work energy principle. Okay, we'll do another problem. But I'm going to stop here. Another problem will be another video.